This is the course Mechanical Vibration, and we continue to study the system under free vibration. We will start now with systems with viscous damping. My name is Carmen Muller-Karger, and we continue with our textbook, RAW, in chapter number 2. This is our system composed by a mass, a spring, and a damper. And this is our free body diagram. We have a displacement that goes downwards, and then we have the force of the spring and the force of the damper. The viscous damping force is proportional to the velocity. It can be expressed with this equation right here, where C is the damping constant or coefficient of viscous damping, and the negative sign indicates that the damping force is opposite to the direction of the velocity, like we show here in our free body diagram. Using the Newton's law, we can get our equation of motion. We are assuming that our x is measured from the static deflection. So, as you recall, when we did analysis for vertical system, the static deflection will be equals to the weight. Therefore, these two terms cancel out, and we have the equation of motion will be equals to the mass times acceleration plus the force of the viscous damper, and we have the force of the spring, and this will be equals to 0. Very similar to the analysis we did for undamped system, we have that the solution for this second order differential equation can be found assuming that the solution has this form, C, which is a constant times an exponential to st. If we derive this expression, we get this expression, and we derive it again, we get this expression. If we introduce all these three terms into our differential equation, we get this expression right here. Since the exponential or the constant cannot be 0, we have that this polynomial, which is called the characteristic equation, have to be 0. When we solve this polynomial, the roots will represent the eigenvalues of the equation. When we solve the characteristic equation, we get two solutions with a solver of a quadratic equation, and here are the solutions. We get this will be the first solution, and with this negative side will be the second solution. Therefore, our solution becomes C1 e to the first solution times t plus C2 e to the second solution times t. This is the general solution of our equation. Now, let me introduce you the concepts of critical damping constant and damping ratio. The critical damping constant is defined as the value of the damping constant C for which the radical of this equation becomes 0. This radical. So we are looking for this C that makes this radical equals to 0. Then we have the concepts of, we already know the one, natural frequency. This is the value for the damper that makes this radical equals to 0, which is 2 square root of the constant of the spring times the mass. And then we have the damping ratio. The damping ratio is defined as the constant of the damper divided by the critical damping constant. So let's transform this equation in terms of these variables over here. To do so, we will do some algebra divided by m, the whole equation first, and C over m become 2 zeta, which is the damping ratio, times omega n. And if we substitute this value in here, we get that we have the acceleration plus 2 zeta omega n velocity plus the omega n squared times the displacement equals to 0. We can also place these solutions of the characteristic polynomial in terms of our parameters, and this will be the solution. Depending on the magnitude of the damping of the system, which will be represented by the coefficient of damping, which is this column right here, we will have 4 different solutions. We already studied when we have 0 damping, which is an undamped system, and we already analyzed that we got 2 conjugate imaginary roots with no real part in the solution. and that type of motion was oscillatory. The second one is when we have the undamped system, when zeta is less than 1, and we get two imaginary roots with real part in the solution. This is the real part of the solution, and this is the imaginary part of the solution, and this is oscillatory as well. The third type of motion is when we have critically damping system. As you recall, we defined the damping coefficient when radical of our solution was equals to 0. Therefore, we have only two real solutions of the system, and they are equal. And this type of motion is not oscillatory. And the last one is overdamped system, when zeta, or the coefficient on damping, is greater than 1. We have two different real roots, and in this case, we do not have an oscillatory motion either. When we have zero damping, we have an undamped system. This is a review because we already analyzed this type of system. We have two imaginary roots, and the system could look like that when we have a spring and a mass, no damper. Our equation of motion is this one right here, and x is measured from the statical equilibrium position. The solution is this one right here when we introduce the roots of our polynomial, and we can expand that using the Euler formula. And since a and b are also imaginary, we can convert that to a real variable by adding those two terms and these two terms. And finally, we have the solution that we can express as a combination of cosine and sine functions, or a single cosine with a phase angle. Those two can be related because the magnitude of this expression is the square root of these two constants, and the value of the phase angle is inverse tangent of b over a. Then, if we apply initial conditions x0 and b0, we get these expressions for a, b, or for the magnitude x0 and the phase angle. This can be plotted as a cosine with the phase angle, and what is very important that we know that this system oscillates at its natural frequency. Its natural frequency being the square root of the constant of the spring divided by the mass. We can read the period right here, which is the time that takes to complete a cycle, and the natural frequency will be equals to 2 pi over that period. Let's move on to the case 2, which is undamped system, when the damping ratio is less than 1. The equation of motion when x is measured from the static equilibrium position gives us this equation right here. This is our system, which is a spring, a damper, and a mass. And the value of the roots, we already know that we have a real part and an imaginary part. And the solution will become, right, a times e to the phase root of our characteristic polynomial plus b e to the second root of our characteristic polynomial. And I will introduce here another parameter, which is damper frequency. The damper frequency, which is omega d, will be equals to omega n square root of 1 minus zeta square. Is this term right here, as you see. Therefore, the solution becomes zeta omega n plus or minus I omega d. We expand these solutions using the Euler formula, but as you see, we have the real part over here that will multiply the sum of cosines and sine. A and b are also complex, but we add in those two complex numbers and subtracting multiplying by I give us real number. We have the solution, then we have this exponential that came from the real part of the solution times cosine and sine, and we can write this expression as a cosine with a phase angle. And we can relate those two expressions because this amplitude is the square root of a squared plus b squared, and the phase angle is b over a. Now let's introduce initial conditions to our equations to find A and B. And we expand the expression right here, and we get the initial condition in displacement. We derive this expression, which gives me this equation right here. And when we introduce the velocity, we get that cosine is 1, sine is 0, and then we get that A is equals to the displacement and B is equals to the initial velocity plus the initial displacement times zeta omega n divided by omega d. We can plot this expression, and this curve is a cosine wave, and what is very particular from this equation is that the amplitude of the cosine function is multiplied by a negative exponential. So this magnitude of the cosine equation decreases over time. Also very important to notice when we read the period, which is the time that elapses between two cycles, this period is called damped period. And then the damped frequency is defined as 2 pi over the damped period. Remember that the damped frequency relates to the natural frequency as natural frequency times 1 minus zeta squared. It can be seen then that the damped frequency is always less than the natural frequency of the system. The bigger the damping ratio, the less the damping frequency. Please notice that the phase angle is calculated as inverse tangent of B over A. If we express this same curve, but instead of using a single cosine with a phase angle, we use a sine with a phase angle, we add the phase angle, that will be here, this angle right here, and the phase angle will be the inverse function of the tangent and will be A over B. So just be careful if you want to use a single cosine function or a single sine function, and you will get exactly the same curve either way if you choose to use a cosine or a sine function. We continue with the undamped system where zeta is less than 1, and we will define the logarithm decrement, which represents the rate at which the amplitude of a free damping system decreases. So we see this curve over here. Let's take the response of the system at two different times, at time 1 and at time 2. The equation becomes then this one for time 1 and this one for time 2. The difference between time 1 and time 2 is the period of the function right here. So t2 will be equals to t1 plus the period of the function. The cosine function repeats itself every cycle. So we can cancel these two terms. We cancel also the amplitude x0. You see we have t1 here, this cancels out as well. And then we get only e to negative zeta omega, the period. And the period, as you know, is 2 pi over omega d. And omega d is omega n square root of 1 minus zeta squared. The decrement logarithm can be then obtained by taking logarithm in both sides of the equation, and this is the logarithm of x1 at t1 and x2 at t2, and it will be equals to this function right here. We can also cancel omega n. So the decrement logarithm is defined as 2 pi zeta over square root of 1 minus zeta squared. We could do the same analysis not for consecutive responses but after n cycles. So we can take the response of t1 and then take it again at tn plus 1, and the solution for the decrement logarithm will be this one right here. So it will be the same, just multiply by the number of cycles we decide to choose to read our response. The logarithm decrement is dimensionless and is another form of a dimensionless damping ratio. Once we know the decrement logarithm, we can find the damping ratio zeta. The logarithm decrement is very useful to find the damping of a system when we have the experimental response of the system. We will measure 2 consecutive or 2 non-consecutive amplitudes, and then we can, with this equation right here, find the decrement logarithm, and we can solve for theta and find the damping ratio. Having this equation for the logarithm decrement, we solve for theta and we get this equation right here in terms of the logarithm decrement. We can also, doing some algebra, write it in terms of the damped frequency. We can write the decrement logarithm in terms of 2 pi omega d times c over 2m. When we have very small damping, we can simplify this equation by 1 minus a very small number becomes 1, and so we have only the upper term, right? And then if we solve for theta, this is for only consecutive responses for one cycle. And then if we plug this equation, we will see that this simplified version is very similar to the one that we have here, but only for very small damping region. Let's now move to the third case, in which we have critical damped system. This means that the damping ratio theta is equals to 1. Remember, that means that the radical of the roots equals to 0, because that's how we define critically damped system. And then both roots are the same, negative real number. Since we have 2 roots that are equal, then we have to solve the system as a to the e negative the first one plus b t e to the second one, which is the same. To find a and b for specific initial conditions x0 and b0, we plug into that for time equals 0, and we find a, and we derive this expression right here, the derivative of the first term plus the derivative of the second term, which have 2 variables, t and e to the minus omega nt. We plug that into our initial velocity and we find b. Finally, our solution becomes this expression right here. As you see, both terms are multiplied by a negative exponential. So this curve goes to 0 eventually and is aperiodic. A critical damped system will have the smallest damping required for an aperiodic motion. Hence, the mass returned to the position of rest in the shortest times possible, without overshooting. The property of critical damping is used in many practical applications. For example, large guns have dash spots with critical damping value, so they return to the original position recall in the smallest time possible. The last case that we will study is an overdamped system, where the damping ratio is greater than 1. The equation is measured again from the static equilibrium position, so we have the same equation. The values of the roots are 2 real solutions, but different. When we introduce that in our solution, we get this solution right here, a to e to the first root plus b e to the second root. When we apply the initial conditions, we get the values for a and the value for b. When we plot this equation, we get that the motion represents an aperiodic function, and eventually this moves to 0, but much slower than a critical damped system. Those doors that have a mechanism that close the door very slowly, those are an overdamped system. Also, the suspension of certain cars or public transportation represent overdamped system, so where we arrive to a stop smoothly goes to the equilibrium position. In this graph, we have the 4 cases that we talked about. The first one is an undamped system, where we have the periodic function that oscillates at the natural frequency, and the amplitude remains constant through the whole motion. Then we have the underdamped, where the damping ratio is less than 1 and the amplitude diminishes over time with an exponential curve. The curve oscillates at a damped frequency, and the damped frequency is less than the natural frequency. Then we have the critical damped system, where the damping ratio is equals to 1. As you see, it goes very quickly to the equilibrium position. And then finally we have the overdamped system, where the damping ratio is greater than 1, and as you see, it goes also to the equilibrium position, but much slower than the critical damped system, and it does not oscillate, so it goes to the equilibrium position without bouncing. Let's calculate the energy dissipated in a viscous damping system. The rate of change of energy with time is given by the force times the velocity, but the force is the damping coefficient times the velocity, so we have the derivative of the displacement squared. Let's assume that we have a simple harmonic motion to calculate the value for the energy dissipated. So we derive this expression to put it here, because this is the derivative of the displacement respect to time. This is the displacement, so we substitute it right here, and then to change the limit of integration, we will integrate respect to the frequency time. So this is our new differential. You see that we change it here, the limit of integration. So we integrate this expression, and we evaluated it in between 0 and 2 pi, and we have this expression right here. As shown, the energy dissipated is proportional to the damped frequency and the square of the amplitude. The energy loss in each cycle can be computed dividing this term, that is the energy dissipated, by the total energy of the system. It could be the total kinetic energy or the potential energy. As you see that the amplitude cancels out, one of the damped frequency cancels out, and we get this expression right here that can be related to the logarithmic decrement and also to the zeta, which is our damping ratio. This term over here is what is called specific damping capacity of a material.